So, hi everyone. I'm Lujie. I just obtained my PhD from MIT Robot Locomotion Group. So, today I'm going to give a talk on bridging model-based and learning-based methods for robotic local manipulation and control. And before I started, I would like to begin with a small story. So, my advisor Russ, who used to be like a hardcore model-based person, he took the scaling is enough side of the debate at Coro 2023. And at that time, I had a small existential crisis. I was asking myself if I was spending my PhD on the wrong side of the history. So fortunately, I decided not to quit. Instead, today I will show you guys that the future of robotics, I argue, lies not in scaling or modeling alone, but in bridging the two. Okay. So in recent years, robot manipulation and local manipulation advanced significantly, enabling robots to perform increasingly complex tasks. For example, in-hand manipulation, such as pen spinning, demonstrates fine motor control in robotic hands. Moving to the top right, TRI has developed robots with dexterous manipulation skills powered by large behavior models, allowing them to perform tasks with impressive autonomy. The integration of locomotion has opened a new frontier. Boston Dynamics eAtlas has leveraged large behavior models to perform logistic tasks with whole body coordination. And in research labs, humanoid robots can learn from human videos to seamlessly couple locomotion and manipulation to carry objects. To equip robots with such dexterous and agile capabilities, researchers have attempted to plan and control through contact with model-based techniques. Classical mechanics perform rigorous mathematical analysis on kinematics, dynamics, motion planning, and control, but does not offer flexible solutions to reasoning about how robots make and break contacts. Existing works based on contact implicit trajectory optimization have sought to formulate the problem into a smooth, nonlinear optimization program. This method offers flexibility for handling contact modes, but suffers from poor global exploration and relies on good initial guesses. Combinatorial optimization overcomes the localness of contact implicit trajectory optimization via more global exploration, but suffers from from explosion of contact modes as the system gets more and more complex. On the other hand, learning-based methods have demonstrated impressive empirical performance. Reinforcement learning enables robots to acquire skills through trial and error, but efficient exploration is highly sensitive to reward engineering. Imitation learning teaches robots to learn from human demonstrations and has demonstrated success in very complicated tasks such as shoelace tying. However, it requires large-scale, high-quality expert data and does not generalize quite well beyond demonstrations. A recent and transformative trend in learning-based control is the application of foundation models to robotics. These models build upon their vision language model predecessors with an action head tailored for robot motions. These foundation models exhibit strong performance in generalization, spatial reasoning, and scene understanding, but their performance is fundamentally tied to the quality and scale of the training data. So at a high level, we've seen both model-based and learning-based approaches demonstrated significant success in robotic control. On the one hand, model-based methods leverage model structures for efficient online and offline compute, and sometimes they come with performance guarantees. However, they often rely on good models and accurate state estimation, and some of the problems are really hard to be formulated into a numerically tractable way. On the other hand, learning-based methods are flexible, adaptive, and expressive. We can readily incorporate perception into the entire pipeline via a visual motor policy, but they often require a large number of samples, which are often also costly to collect. And they also lack the performance guarantees, which might be critical for safety essential applications. So in this talk, I would like to address the question, how do we leverage the advantages of model-based methods to help address the problem of data scarcity and lack of performance guarantees for learning-based methods? By the way, I welcome questions during my talk, so feel free to ask me any questions if you want. So in this talk, I will talk about my projects on improving data-driven policies with model-based techniques from two perspectives, providing performance guarantees and efficient data generation for learning-based policies. I will start with the first perspective, embedding control theoretic principles in learning-based controllers via neural Lyapunov control, which brings interpretability and stability guarantees to learned policies. Building on the understanding of dynamical systems, I will then discuss how to leverage model structures to efficiently generate data for more complex robotic systems. I will talk about how we can use trajectory optimization to generate large-scale, high-quality datasets for training robust and performant policies for dexterous manipulation. Finally, I will conclude with extending data generation to whole-body local manipulation via interaction-preserving constraint optimization. So, one of the major limitations of purely data-driven policies is their lack of performance guarantees. My first contribution tackles this by embedding control theoretical guarantees directly into the learning process. Let's consider a self-driving car running a neural network policy. We wanted to safely carry the passengers without crashing. Ideally, such a policy should come with formal guarantees. In practice, however, neural network controllers often perform well empirically but lack provable safety guarantees. To address this, we leverage Lyapunov stability in control theory. Lyapunov function can be thought of as a ball-shaped energy function that measures how far the system is from the equilibrium. As the system evolves, the Lyapunov function's value should continuously decrease, guiding the system towards a stable equilibrium. Previous works have synthesized Lyapunov stable neural controllers, but only for state feedback systems due to the scalability challenge. We take the first step towards extending such formal guarantees to higher dimensional output feedback systems, where the robot perceives the environment through vision, LiDAR, or other sensors. Our goal here is to jointly synthesize a neural network controller, observer, and a Lyapunov stability certificate. We also perform a rigorous post-hoc neural network verification using efficient GPU-accelerated complete neural network verifier. To enable this, we propose a novel training and verification formulation, which was inspired by convex optimization. Such novel formulation is easier to train and verify and afford control over region of attraction growth during training. Region of attraction here is the guaranteed region where the learned policy is guaranteed to work. So let's look at the definition of a Lyapunov function mathematically. The function itself should be positive definite, and its time derivative should be negative definite. And these conditions should hold for infinitely many x on a region we care about. I will present our formulation step by step. We satisfy the positive sumitiveness by construction and train and verify neural Lyapunov functions for the time derivative condition. So let's take a look at the formulation step by step. So first, the orange ball, we define it as to be the guaranteed region of operation in prior works. Our verification formulation defines a strictly larger verifiable region of attraction, and while combined with our training formulation, can result in even larger region of guaranteed operation. So how do we achieve this? We manipulate the Lyapunov time derivative condition to turn it into an OR statement. This trick actually eliminates the verification of the unnecessary condition outside the region of attraction. To sketch our formulation idea, I will do a little bit of math. Consider this two-dimensional double integrated dynamics And we are interested in the region, which is the square around the origin. The controller pi of xt equals negative xt is a stabilizing controller with the quadratic Lyapunov certificate x transpose x. With a bit of more algebra, we can see that the Lyapunov time derivative condition is satisfied on the entire square. Previous methods defined the region of attraction as the largest sublevel set within the square, which is this yellow circle, while our method defines the region of attraction as the largest invariant set within the square, which is the entire square itself. This way, we can see that our verification formulation is a strict superset of all the previous methods. The verification formulation can also guide the training process, which will result in a certificate-guided training framework. Starting from a collection of randomly sampled states, we roll out the dynamics forward for a single time step and feed the observation to the state observer. The controller then takes both the observation and the state estimation to decide the control action to stabilize the system dynamics. The system states are then state estimation are then fed into the Lyapunov function to check the Lyapunov stability condition. If the stability conditions are violated, the counterexamples xt are added back into the data buffer, and the parameters of the neural network controller, observer, and Lyapunov functions are updated via backpropagation. This process can essentially be viewed as an efficient data generation pipeline where the training is actively guided by stability violations rather than just random sampling in reinforcement learning. Here also, Lyapunov function plays a kind of a role like critic in the standard RL literature, while we ensure formal guarantees with a complete neural network verifier. So after the training converges, we use a complete neural network verifier to certify all the trained networks. So this verifier provides a formal guarantee that the stability condition holds for infinitely many x on a compact region, in contrast to just probabilistic or empirical certificates. So here we show that our neural network policies trained and verified using our formulation for two simpler dynamical systems, inverted pendulum and path tracking. Here we show that our region of attraction is actually a strict superset of all the baselines. And moving forward to like a bit higher dimensional systems with more challenging observations, we also validate our approach on the task of steering a 2D quadrotor to cruise at a constant height, and the quadrotor obtains the observations from a LiDAR sensor. So this is a toy example we built to capture the essence of an output feedback systems with general observations. And the first time such system can be formally certificated with neural network verifiers. So here we show that, again, the black contours represent a 2D slice of the decently large certified region of attraction. So the neural Lyapunov work I just present is kind of a reflection of my interest in rigorous control theoretic analysis for simpler dynamical systems early on in my PhD. As my research evolved, I became more increasingly interested in unlocking the potential of more complex manipulation and loco-manipulation systems. Specifically, my recent work explores how to efficiently generate large-scale, context-rich datasets through trajectory optimization. I'm going to pause here and see if there are any questions about the neural Lyapunov control work. Okay, go ahead.
I think you have like a, can you hear me?
Yes.
Yeah, I think you have like a stability verification at the in your data generation pipeline.
Mm-hmm.
So how so can you give us some examples, and how does it scale for like more complicated systems?
Yeah, that's a good question. So the Scalability issue is always a challenge. For There's a trade-off between verifiability and the capability of the trained policies. So, for example, for higher dimensional locomotion systems like quadruped or humanoid, it's already hard to synthesize a policy, and it's even harder to actually formally certify the policies for the higher dimensional systems. So we are actually working towards the formal certificate, but I think rather than like a deterministic guarantee, it's more likely to provide more probabilistic or empirical certificate. So I think for a higher dimensional system, yeah, that there is definitely a trade-off between verifiability and capability for complex systems. Yeah.
So in this case, so what are the examples for the stability conditions for the several systems you have shown?
Yeah, so mostly the systems are like simpler dynamical systems, like just autonomous vehicles. If you want to make the vehicle follow the lane without crashing, or like steering a quadrotor to cruise at a constant height. So which is like essentially kind of more simpler dynamical systems with I would say smoother dynamics.
Okay, so basically you can manually write down those stability conditions and
Uh, yes,
try or
that's a
check
good
in
point.
simulation or yeah, I'm just curious, like how did you came up with those conditions?
Yeah, so if we want formal stability certificate, we need the closed form solution of the system dynamics. That's admittedly like a classical control, like canonical requirement. And yeah, admittedly, it might be harder to write out the dynamics in closed form for like let's say contact dynamics, where time stepping the simulator might be more feasible.
Okay, okay, cool.
Yeah, thanks for the great question. So I will go ahead to like move on to like higher dimensional, more complicated manipulation systems. So here the problems I'm trying to address is the data scarcity issue. Previously, researchers have tried to develop many methods to address these data scarcity problem. One of the most popular one is physical data collection, with either thousands of humans teleoperating large robot fleets or exoskeleton devices. However, collecting internet-scale robotic datasets remains time-consuming and costly, requiring an impractical amount of human effort and resources. On the other hand, significant effort has been devoted to automating the data generation process through data augmentation techniques, either leveraging kinematic replay in simulation or state-of-the-art generative models for semantic and visual augmentations. However, efficient data generation for context-rich tasks still remains underexplored. So to address these issues, we introduce a cost-effective data generation pipeline that uses trajectory optimization to augment human demonstrations to a distribution of tasks. Human demonstrations offer valuable global information for solving complex long-horizon multi-contact tasks, but can be costly and difficult to collect. Trajectory optimization has demonstrated success in generating locally optimal trajectories for contact-rich tasks, but they often rely on global guidance in the form of good initial guesses. In this project, we leverage the strength of both to generate a large, dynamically feasible datasets that generalize across embodiments, physical parameters, and initial states. So we call our data generation framework PhysicsGen. PhysicsGen starts with a small number of human demonstrations collected in a virtual reality simulation environment. We then refine these demonstrations using optimization-based kinematic retargeting and trajectory optimization to adapt them across various robot embodiments and physical parameters. This process results in a diverse, physically consistent dataset that enables cross-embodiment data transfer and training robust policies that achieve high success rates in sim-to-real hardware deployment on bimanual EWA arm. Our data collection pipeline is a human hand demonstration interface in VR. So here, the right video visualizes the real-time view in the virtual reality environment. Our demonstration interface is very fast and cost-effective. It takes about 7 minutes to collect 24 long horizon demos for each considered system, including a floating Allegro hand, bimanual and bimanual robot arms. So after we collect the human demonstrations in VR, we try to retarget the human motions onto the kinematic motions of the specific robot embodiment in simulation. So here, including a floating Allegro hand, bimanual EWA arms, and bimanual Panda arms. So here, the left side visualizes the two fingers manipulating a small cube, which is 6 centimeters. And the right are retargeted to the configurations of two larger bimanual robot arms flipping a large size box, which is 30 centimeters. Here, given a sequence of demonstrations, we aim to find the robot state's X-ray target, which is essentially the robot joint angles. And for the floating Allegro hand, it also includes the floating base pose. We want to find the robot states that match the positioning of the demonstrators by minimizing the distance between corresponding key points. So here, the phi's are the manually selected correspondences. For example, the blue spheres in each of the embodiment illustrate the demo hand landmarks scaled to the specific systems. And for the bimanual EWA arm, the phi's can correspond to the left end effector as well as the left fingertip. We also enforce non-penetration constraints between all collision pairs, including robot object and between the robots, as well as joint limit. So solving this optimization, we are trying to kinematically retarget the human motions collected in VR to the specific robot embodiments. The kinematically feasible robot states, X-ray target, are generally not dynamically feasible due to the embodiment gap and differences in physical parameters. We use trajectory optimization to locally refine the kinematically feasible trajectories. Here, the objective is to match the demonstration while minimizing the control effort. Similar to the kinematic phase, we enforce non-penetration and joint limit constraints, and additionally add dynamical and input constraints. And thanks to the access to the system dynamics F, we can locally perturb the physical parameters as well as robot and object states around a nominal demonstration. So per Xianyi's point before, the dynamics here, we don't require analytic form or closed form. For my specific implementation, we're just simply time stepping the simulator. So with this formulation and trajectory optimization formulation, from a single demonstration, we can solve this optimization program for a distribution of tasks with different dynamics, where theta here represents all the perturbations, including object size, friction parameters, masses, as well as robot configurations and stiffness, and so on. So here, this slide visualizes the human demonstration in VR in the left column. The middle column shows the kinematic replay, which most of the time fails the task, and the right column demonstrates the dynamically feasible trajectories after trajectory optimization. Notice that both the EWA and Panda arms can leverage the same human demonstration to accomplish the manipulation task. While kinematic retargeting of demonstrations might suffice to generate data for simpler manipulation tasks such as pick and place, trajectory optimization is very crucial for ensuring dynamic feasibility for contact-rich systems. Here, we show that trajectory optimization is crucial for generating diverse trajectories. It can efficiently augment a small set of demonstrations to a wide distribution of trajectories with locally perturbed physical parameters and initial states. We validate our approach by training behavior calling policies on the generated datasets. we trained diffusion policy on 24 original demo trajectories, as well as 500 augmented trajectories. Here, the latter is shown to be more robust and performant, achieving higher success rate across all platforms, including the floating Allegro hand, bimanual EWA, and Panda arms. So here's an example of the floating Allegro hand. The baseline policy trained on 24 original human demonstrations easily encounter out-of-distribution states and fails the task, while the policy trained on 500 generated trajectories keeps trying to establish contact with the cube even after initial misses. It keeps trying and finally succeeded in making the contact and accomplished the task. We also deploy the trained policies directly onto hardware using this fixed base bimanual EWA arms without any real-world fine-tuning. The arms performed a sequence of coordinated rolling, pitching, and yawing actions to reorient the box to the goalpost. This is a very long horizon manipulation task that is very challenging. It requires the robots to frequently make and break contact with the object and requires precise control, because small positional errors can result in missed contacts, which in turn lead to task failure. Here we show the policies trained on the augmented datasets can employ a firmer grasp to prevent the box from sliding further. But sometimes it can still make undesired contact with the box due to unmodeled collision geometries or state estimation errors. However, thanks to the diverse augmented datasets, it can quickly recover. So I have talked about how to use trajectory optimization to generate high-quality datasets for manipulation. A natural question would be, can we extend this to whole-body local manipulation? The challenge of local manipulation lies not only in coordinating dynamic locomotion with contact-rich manipulation, but also in the fact that these two capabilities are often developed using separate toolchains and learning paradigms. For example, we've seen robot arms cutting an apple, repairing a bike wheel using imitation learning, as well as unitary robots dancing using reinforcement learning. But so far, we haven't really seen reliable and scalable systems that integrate both imitation learning for manipulation and RL for locomotion in a unified way. In order to bridge this gap, in this project, we propose a principled interaction-preserving data generation engine for local manipulation. So let's try to revisit the automated data generation pipeline for manipulation and adapt it for local manipulation together. Starting with a single human demonstration, we converted into a physically realistic trajectory for the robot using kinematic retargeting and trajectory optimization. We then adapt the same reference motion across various robot embodiments and physical parameters to generate a large-scale whole-body local manipulation dataset for training robust policies for sim-to-real transfer. Now we have an automated data generation pipeline for locomotion, and we can claim success. Is it that easy? The crux here, I find, is kinematic retargeting. Existing retargeting pipelines often produce physically implausible artifacts like penetration with the ground and the object, as well as food skating. And more importantly, it lacks the interaction preserving mechanism that is essential for expressive local manipulation. In fact, there is a lack of principled high-quality retargeting framework for humanoid whole-body control. With suboptimal reference motions, practitioners are forced to either manually clean the data or introduce extensive reward engineering to compensate for these artifacts. To address this, we introduce Omni-Retarget, an interaction-preserving data generation engine that explicitly models and preserves the crucial spatial and contact relationship between an agent, the terrain, and manipulated objects, while enforcing kinematic constraints. Moreover, preserving task-relevant interactions enables efficient data augmentation from a single demonstration to different robot embodiments, terrains, and object configurations. So one of the most popular approaches to kinematic retargeting is key point matching, which minimizes the Euclidean distance between the demonstrator and target robot's key point positions. For locomotion tasks, researchers can compensate for lower quality kinematic references with extensive reward engineering in RL. But for local manipulation, that's not the case. The robot must maintain contact with the objects, and such approximations can easily break down. For instance, because the robot can be much shorter than the human demonstrator, directly scaling their key points to the robot size often results in penetration. In this project, we leverage the interaction mesh, which is a volumetric structure to preserve spatial relationship between body parts, objects, and the environment. Assuming that we have access to the shape and pose of the human demonstrator and the manipulated object, we want to retarget the human object motion to the robot object motion. To construct the interaction preserving 3D meshes, we select key joints on the human and corresponding semantic joints on the robot. We then sample points in the object and the terrain and use the same set of points for the robot as well. Ideally, we would like to identify the exact contact points through simulation to best preserve contact relationships, but we find our method is already quite robust to the precise placement of these points, and we just use random sampling for simplicity. The set of human and object key points constitute the source vertices, while the corresponding robot and object key points form the target vertices. We use a special technique called Delaunay tetrahedronization to connect nearby points to construct the mesh. This kind of tetrahedronization technique favors connecting nearby points while avoiding occlusions. This mesh allows us to define the Laplacian coordinate of a vertex as its displacements relative to neighbors. We compute the source and target Laplacian coordinate and try to minimize the deformation between the two. By minimizing the Laplacian coordinate deformation, we try to keep every vertex in roughly the same configuration relative to its neighbors. This way, we can preserve the crucial spatial and contact relationship between an agent, the terrain, and manipulated objects. Here, we try to seek the robot configuration QT, consisting of the floating base pose and all joint angles, that minimizes this Laplacian deformation energy and a cost that encourages temporal smoothness. It also enforces the non-penetration constraints for all the collision pairs, as well as joint limit and velocity limit. We also enforce a hard constraint to prevent the stance foot from sliding. So here is a visualization of the interaction meshes used to calculate for the source human demonstrator and the target robot for this box carrying task. The blue dots are the human or robot key points, while the green dots are the sampled points from the object surface. Yeah, I just want to show it again to visualize how these interaction mesh work in real. So this is our first attempt at building a principled interaction-preserving kinematic retargeting pipeline, and we believe that many of its design choices can be further improved through more rigorous analysis and experimentation. But we find our current implementation is already producing reasonable performance, and we also encourage people people to use it. So here, this nonlinear optimization denoted by star is the core optimization program for our interaction preserving retargeting framework, which we call OmniRetarget. One of the key advantages of our framework is its capability for systematic data augmentation, which eliminates the need for collecting numerous repetitive demonstrations with minor spatial variations. We generate diverse interactions by augmenting both the object's spatial configuration and its shape. We apply translations and rotations to modify the object's initial pose, as well as scale the 3 dimensions of the object. For each new scenario, we resolve the optimization. By minimizing the interaction mesh deformation, we find a new kinematically valid robot motion that preserves the essential spatial and contact relationships of the original interaction. OmniRetarget also adapts to different robot embodiments, including the Unitree G1, H1, and this booster T1. We also generate diverse terrain scenarios by scaling the environmental features, such as varying the platform height and depth. So here, the top left corner is the original demonstration, while all the other ones scale the terrains to either shorter or taller than the original platform. Now, let me present the automated data generation pipeline for local manipulation. Human demonstrations are retargeted to the robot via interaction mesh-based constraint optimization to produce kinematically feasible trajectories. A new optimization program is solved for each spatial and shape augmentation, producing diverse local manipulation trajectories. Having established our method for generating high-quality kinematic references, we use imitation-guided RL to bridge the gap to dynamics by training a low-level policy that converts these trajectories into physically realizable actions, enabling zero-shot transfer to real-world humanoids. So the clean formulation of OmniRetarget enables a minimal RL training formulation. We know that reward engineering is often the main difficulty in humanoid RL. For example, prior works rely on many ad hoc regularizers, such as contact time and foot flight, to compensate for artifacts in noisy references. But tuning these terms is very tedious and fragile. The high-quality references generated by OmniRetarget enables a minimal and unified training formulation, only 5 rewards, and a purely proprioceptive observation space shared by all tasks. Ultimately, OmniRetarget demonstrates a paradigm shift from patching lower quality reference motions with complex reward engineering to solve the problem at its core with principled data generation. Kinematic quality here directly impacts the RL performance. So we select 40 challenging motions for OmniRetarget and many baselines, including PHC, GMR, and video mimic. OmniRetarget, which is this blue bar, significantly outperforms all baselines across all kinematic metrics. So achieving the smallest penetration, no foot skating, and the best contact preservation. Consequently, OmniRetarget's downstream RL policies achieved the highest success rate across all tasks. The interaction preserving property of OmniRetarget generalizes a single box carrying demonstration across multiple spatial configurations and object shapes. So here we see like the robot can pick up objects from different spatial configurations as well as different sizes, but you only need a single human demonstration for achieving that. In comparison, relying solely on domain randomization to perturb object shapes and pose during RL training performs poorly because the policies struggle to explore far beyond the nominal reference. The motions augmented for different terrain heights can also be used for training and deployment effectively. Notably, these augmented motions transfer to hardware without reward tuning, efficiently expanding the repertoire of scenes and behaviors we can achieve in the real world. So this is 0.5 playback. OmniRetarget also enables diverse box carrying skills with various picking and walking styles. It also enables diverse scene interaction, including crawling, climbing, and stepping.
Do you also select key points in the fixed environment?
Um,
Sorry, can you hear me?
yes, yes.
Yeah, my question was, do you also have key points for the fixed environment or it's more on the movable objects?
Yeah, so for this scene interaction task, we select key points on the terrains, on these like platforms and tables. So yeah, I'm just using the human object task as an example, but similar things are done for terrains as well.
Okay. Another question is that, I may have missed it, but do you have any terms that try to enforce contacts?
Yeah, that's a really good question. So here, the contact relationship is not explicitly preserved. We hope that this deformation, like minimizing the deformation in Laplacian, will help us preserve the contact relationship because these Laplacian is basically saying for example, there is an edge between the human wrist and the object surface. So we want the human wrist of we want also want the robot wrist to be close to the object surface, and minimizing this Laplacian deformation hopefully will enable us to do that. But that's of course a kind of a soft way to enforce that. But because I wrote my own as it's actually sequential SOCP solver for this non-convex program, we can mostly reduce this cost to like 10 to the negative 3. So mostly the contact relationship are kind of implicitly preserved, but in a numerically very favorable way. Yeah.
Sorry, which term you said like reduced to like very low?
This Laplacian deformation minimization.
And is this, I'm asking this because we have students working on like whole body contact.
Hmm. Right.
Um, so I feel like maybe has some like implicit assumption that the contacts are made on the wrist area or on the foot area. So do you see any, yeah, that's the first question. Do you think that's true or false? The second question is that, um, does the complexity of the problems scale significantly if you select more key points on the body? Yeah.
Hmm. Yeah, that's a great question. So first of all, for whole body contact, here this is just for illustration. I'm selecting like maybe shoulders, wrist, and foot for like constructing this like simpler tetrahedron. But this is the actual mesh that we're using, which selects more key point on the robot body. So if one cares more about like whole body contact, maybe one can definitely select more key points on the body. And as for scalability, I think this program actually scales reasonably well with the number of key points. We can so um, for the object, we can easily scale to like 50 or 100 key points on the object, and the solve time will be like milliseconds per time step. And I forgot to mention, we solve these program like frame by frame. So we solve this program for T and use Qt optimal as the initialization for the next time step T plus 1. So we solve these like frame by frame. So for each frame, it's like pretty fast. So I think the scalability is pretty promising for even for selecting more key points. And another point is that this procedure is kinematic retargeting, which doesn't quite consider dynamics. If we want the whole body contact to be dynamically feasible, later RL will kind of help us resolve this issue by doing like object tracking or robot keyframe tracking. So that way, I think RL will help us close the dynamics gap.
Oh, good, thank you.
Yeah, great question. So yeah, I think I was showing part of this demo. So here is a forward rolling demo. And finally, a wall flip. So this is very highly dynamic. The robot reaches a maximum linear velocity of 3.5 meters per second and a peak angular velocity of 15 radians per second. So in conclusion, I talk about my projects on improving data-driven policies with model-based techniques from two perspectives, providing performance guarantees and efficient data generation for learning-based policies. I talk about how to embed control theoretic guarantees into the learning-based policies using neural network control, as well as how to use trajectory optimization to synthesize large-scale, high-quality datasets for dexterous contact-rich manipulation. And finally, I talk about how to use interaction-preserving constraint optimization to generate dataset for humanoid whole-body loco-manipulation. So moving forward, I'm thinking about like expanding this data generation framework to be more general to handle manipulation, locomotion, and local manipulation tasks. This data generation framework should be agnostic to any upstream data sources, including teleoperation, mocap, or even larger scale internet videos. And this data generation framework can leverage either omni-retarget for kinematic retargeting, as well as physics-gen like trajectory optimization to produce high-quality, large-scale datasets. And downstream, the framework should be agnostic to acceptable to like different learning paradigms, including behavior cloning, RL, or even the certificate guided training we talk about. And with this, we hope to train the next generation of robot foundation model. And finally, I want to also emphasize that my talk have been focusing on the vertical axis of equipping robots with dexterity and agility, which is the physical intelligence needed to act skillfully in the world. But there is another essential axis, cognition. Today, large vision language models trained on massive internet-scale data have given robots remarkable reasoning capabilities from the rich world knowledge. For example, we've seen Gemini Robotics, Pi 05, showing impressive reasoning capabilities. However, these models lack the abundant embodied experience, the scale or resolution needed for fine-grained motor skill. I believe the next frontier lies in synergizing the two. So, as my title suggests, I believe that the future is combining the scalability of data-driven learning with the structure of model-based reasonings to let the intelligence of physics and cognition pass in between two to create truly intelligent agents. Ones that not only see and reason, but also act with dexterity and agility in the real world. And that concludes my talk, and happy to take any further questions.
Yes, thanks for the talk. Yeah, if you wanted to ask a question, it would be great to come closer to the camera, so we can hear. Any questions? So Lujie, I think you mentioned about, I really like the ending on like the cognition and the motor dexterity.
Mm-hmm.
So how did you envision that the communication between this cognitive dexterity and the manual dexterity?
Yeah, I think it's a very good question. So, um, I think there are like different way, and of course it's a very challenging one. So I think there are different ways to do it. So for example, we can do well, we can have a hierarchical framework where like the higher level vision language models or of VLM try to give like a higher level reasoning or higher level semantic plan, and lower level we have this like lower level policies for tracking or reactive control with dexterous and agile capabilities. But I think more importantly, we also want to make this information flow because I think right now most of the VLA just like keeps querying the VLM without correcting like the its internal understanding of the world. I think the internal understanding is like kind of embedded in implicitly in the weights. We can also try to think about like using more explicit representation, such as like instead of just using RGB, we can have like a 3D understanding of the world, or we can use some maybe adaptive control notion to make the like the large model refine its belief about the world, either it be like friction coefficient or like the depth or the more fine-grained detail that is required to accomplish more complex, more challenging, and more context-rich tasks in the real world.
Thank you. And can you go back one slide?
This one.
Yeah, so I'm curious like about this like general data generation. So what do you think are the most important gaps that you're interested to solve for like let's say the next 2, 3 years?
Yeah, I think, yeah, that's also a great question. I would say, still data diversity and quality, fidelity. So, right now, most of the data sources I talk about are like, from mocap, which is a more controlled setting. We have to like wear mocap suits to perform the task, and it's less scalable. If it's probably not possible to wear the mocap suit and demonstrate every single task in household. So we're thinking about like leveraging the internet video data with, and also more importantly, it comes with perception, where there's like egocentric human video, we can and as well as tutorials on how to actually, for example, make the tea or cook the food. So how to leverage like internet abundant internet video, which are actually lower quality to produce like similarly high quality as well as more diverse data, I think is a very important part. And also I mentioned perception. So how to so right now, we essentially here, our policies is either state-based for the manipulation task or completely blind for the local manipulation task. So how to integrate perception into the pipeline in a way that enables more intelligent and diverse task is also, I think, a very interesting topic.
Okay, thank you. I want to check if we have any other questions from the students. If no, I'll just ask one last question.
Uh-huh.
So I think you mentioned about like the pivot from doing from a more like a model-based person to like fully embrace this like learning-based trend. So I'm just curious about like your pivot and what advice would you give to students who are who, for example, might want to pivot or interested in exploring completely new directions.
I think it's a very great question, and it also depends on what one wants to do. Does one want to be more like scholarly, or does one want to be more practical? So I think during the first half of my PhD, my work are mostly more like scholarly and mathy, like doing guarantees, control theoretic guarantees, optimality, stability, and so on. But as my PhD progresses, I wanted to make things work to be more practical. So I do this pivot in the sense that I have a like my strength and my interest are still more grounded in model-based optimization stuff, but I see also the capabilities of generalization and adaptiveness, expressiveness of learning-based methods. So I think try to one of the advice is try to pinpoint some like cons or disadvantages of current learning-based community and try to think if we can use more principled and model-based knowledge to solve it in a more systematic way. So that is also my motivation for omni-retarget. So as I shown in the video here, the learning-based methods or learning community didn't really care much about like hard constraint enforcement or like the more detailed interaction preserving like capabilities. But from model-based optimization standpoint, I think all the retarding pipelines should be rewritten and they should be more principled, higher quality, and model-based optimization can do this in a higher quality manner than like say the learning community's baselines. So that's how I actually came up with the solution, as well as try to combine the advantages of both model-based optimization as well as the impressive RL capabilities for downstream tasks.
Okay, thank you so much, and let's give it another round of applause.
Yeah,
Yeah,
thank you, Shane.
Okay, yes, I haven't. Okay, hi, thank you so much for sharing your wonderful work. And yeah, we're about to at the time for the next talk. So yeah, thank you and see you.
Thank you, Shane. Bye.
Bye.